Right, so the first thing we're going to look at in this video about electrolysis is what oxidation and reduction actually are before we start going into the actual process of electrolysis. So oxidation is defined as the loss of electrons from a substance, and reduction is defined as gain of electrons. Now the way to remember that is oil rig, oxidation is loss, reduction is gain of electrons. Now in terms of electrolysis, what you will find out later in this video is that electrolysis is carried out on ionic substances, and as you know, they're metals and non-metals joined together. And what you will know from the previous ionic bonding video is that they form an ionic lattice in which the positive and negative ions attract each other electrostatically. And these attractions are very, very strong. So it requires a lot of energy to break these electrostatic attractions. Now, we're going to take a look at some of the properties of ionic substances, starting with lead bromide. Now this is ionic, and we're going to check the conductivity and see if it conducts electricity in the solid state. So what we do is we take the solid and we place electrodes in it, and we turn on the electricity, and what will happen is the bulb doesn't light up. And that's because the ions are not free to move when they're in solid state. So it doesn't matter how much we try, the substance will not conduct electricity because the ions are fixed in the solid position and they're unable to move. So the light bulb will not light up because the ions are not letting the electricity flow. So what can we do? Well, the first thing we can do is we can melt the ionic solid and heat it up with a Bunsen burner, and that will melt it. And what that will do is that will allow the ions to then conduct electricity because they're now going to be free to move. And you'll see in this next little section that the ions are flowing, and that is because they're now molten, so they're not solid anymore. Because they've been melted, they're a liquid and the ions are now free to move. And that's important because that allows the electricity to flow. Now if we look at our second example with sodium chloride, as you would expect, if we take some solid sodium chloride and try and pass electricity through it, we're not going to get any joy because the ions are in a fixed position, solid state, they're unable to move, therefore it's not going to conduct electricity and the bulb won't light up. What we can do, different to melting it, is we can dissolve it in water. Now most ionic substances dissolve quite well in water, and when we do that, what we allow is the ions to move. And again, this time the electricity will be allowed to flow because the ions are free to move because they're dissolved. And as you can see, they're moving quite readily in the water, and that's allowing the conductivity and that's allowing the bulb to light up. Right, so just a quick check of these first of all. Molten lead bromide should conduct electricity. Molten aluminium oxide, again it's ionic, it's molten, it should conduct. Solid lead bromide, solid ionic, will not conduct. Solid copper sulfate will not conduct. Copper sulfate solution is basically copper sulfate dissolved in water, so that will conduct. Sodium chloride solution will conduct because again it's dissolved in water so the ions can move. Sodium chloride crystals will not conduct, and the rule is if they're molten or dissolved in water, then the ionic substance will conduct electricity. If they're solid state, then they will not. Right, okay, so electrolysis, the process. The first thing to remember is a little sort of acronym to let you know what the names of the electrodes are. Now I like to use the phrase panic, and that is positive anode, negative is cathode, and that's a little way to remember which electrode is which. That's their proper name, the anode and the cathode. And panic should help you to remember that the positive is the anode and the negative is the cathode. The second thing that you need to get familiar with is this table. Now this table is given to you in the exam. It will be on the back of your periodic table. It tells you all the charges of all the ions. Now most people look at this and think, what use is that to me? I have no clue what this is all about. Well, this is going to be very useful to you because what this is going to allow you to do when you carry out electrolysis, it will allow you to see which electrode the ions are attracted to. Now I'm going to tell you now, before we even start, that If an ion is positive, then it gets attracted to the negative electrode. If an ion is negative, then it's going to get attracted to the positive electrode. And because you've got this table, you can basically see whichever ion you want, you can see which electrode it's going to go to. And it's very straightforward then to be able to understand electrolysis because of this table. Right, the first process we're going to look at is the electrolysis of lead bromide. But before we go into that, we need to just define what electrolysis is. Now, electrolysis means using electricity to split a compound. It's a Greek phrase. Using electricity, electrolysis, to split. So it's splitting a compound using electricity. Now, we use it for many things: purifying copper, plating gold and silver onto jewellery, extracting metals such as aluminium, and also making chlorine, hydrogen and sodium hydroxide, which we'll show later on in the video. So, in electrolysis, the substance that the current passes through is called the electrolyte. Now, as we showed previously, the electrolyte has got to be either dissolved ionics or molten ionic substances. You can't have a solid electrolyte because it won't work. And the electrolyte will contain the positive and negative ions, and they will then be attracted to the appropriate electrode, positive and negative. So first and foremost, the negative ions will move to the positive electrode. Negative attracts positive, and when they get there, they will lose electrons. As we know from earlier, this is oxidation. Because of oil rig, oxidation is loss of electrons. At the negative electrode, we'll get the positive ions moving towards that, and the positive ions are attracted to the negative electrode, and when they get there, they gain electrons, and as we know from previously, that is reduction. So we're going to take a look at a little example now, see if we can clarify what's going on. Right, we've got lead bromide in front of us now. Now, before we start doing anything, the first thing you would do if you get an electrolysis question is you would get out your data table. So you get that table out. Now, that table will help you deduce which ions are going to get attracted to which electrodes. So we're going to start off and take a look. We've got, if we look at our diagram, we've got lead bromide. So what we're going to do, we're going to find lead on here, and lead is there, it's Pb2+, and bromide is there, it's Br-. So we now know the charges of both the ions. So what we know is that lead is positive and bromide is negative. So immediately I now know that the lead is going to be attracted to the negative electrode because lead is positive, and the bromide is going to be attracted to the positive electrode. So when we play the video, it will talk us through what happens. Now, heat it up to melt it to allow the ions to flow. Without that, we're not going to get any movement. So we need to melt the ionic substance. Now, as you can see, you're getting a gas being given off here, and that's bromine. And then at the negative electrode, you'll be getting lead deposited there. So we've got electrolysis here, splitting up a compound, lead bromide, into its elements. And what's happening is the bromide, being negative, is being attracted to the positive electrode and being given off, and the lead is being attracted to the negative electrode. Now, what happens is the ions obviously move to the appropriate electrode. Now, you would only know this information if you'd been and looked on your data table. Without this table, you're not going to know that Pb is 2+ and that Br is minus. You're not expected to remember these. You're just expected to pick them off the table and realise which electrode they get attracted to. So, as we carry on, the substances will form. The lead will go to the negative electrode, it'll gain electrons, and that is reduction. That always happens at the negative electrode. They always gain electrons, so it's always reduction. And what you'll realise is it's always metals that get attracted to the negative, and it's always metals that undergo reduction. So the bromine, or the bromide, then gets attracted to the positive side, and that then helps you to see what's going on with this. That forms bromine gas. So that is electrolysis of lead bromide, and what you'll get at the end of it is bromine gas given off, and if you then tip that out, you'll actually find there's some lead in the bottom left underneath the negative electrode. So you've got lead and bromine back from your electrolysis. It's pretty simple. If you look at the compound that you're going to electrolyse, remember what we said at the start, electrolysis is using electricity to split. Well, you've split lead bromide into lead and bromine. And the key is knowing which element goes to which electrode, and you can do that just by looking at your table. Right, the other thing that's for higher tier is the equations. Now, if you are doing higher tier, you're going to need to learn these two. The examiner will expect you to be able to recall the two equations for the electrolysis of lead bromide. Now, the first one is at the negative electrode. Of course, we know the lead 2+ gets attracted there. It gains 2 electrons to become lead, and that's reduction. Reduction is gain. And at the positive electrode, the Br- becomes Br2 and loses 2 electrons, and that's oxidation. But this section is only for the higher tier. Overall equation is PbBr2 goes to Pb plus Br2, and that's the overall electrolysis process. Right, so that's lead bromide done. Now, the second process that we've got to know is aluminium electrolysis. Now, this is a very, very similar idea. What happens is aluminium oxide or aluminium ore is electrolysed in order to make aluminium. Because as we said earlier, electrolysis will break any compound into its constituent elements. Now, one of the problems with this electrolysis process is that aluminium ore has a very, very high melting point. It's 2050 degrees. That's really high. So what happens is they add a chemical called cryolite to the aluminium oxide, and what that does is it lowers the melting point down to about 700 degrees. And what that does is it saves in terms of cost, because you don't have to use as much electricity because of this lower melting point. It also saves on the emissions as well, because less carbon dioxide is given off because the temperature is lower and less energy is needed. Right, so the same thing happens as with lead bromide. You've got aluminium oxide. The first thing you should do when you're carrying out electrolysis, you should be looking straight to your data sheet. Let's have a look what's going on. So over here, we look down the positive ions and we can find the aluminium is there. Its charge is Al3+. If we look at the oxygen, we can see that it's there, it's negative, so that's good news. We've found both our ions. And then it's just a simple case of realising that positive attracts negative. So we put the solid in there, and you'll see now, the first thing you'll probably realise is that the positive electrodes are in the centre and the negative electrode is sort of around the casing of the container. Now, these electrodes are made of graphite for aluminium oxide electrolysis, and the reason for that is because graphite, as you'll know from the previous sections, is a good conductor because it's got delocalised electrons, and secondly, the reason why it's used in this process is because it's got a very high melting point, so it can withstand the high temperatures that we're going to use. And those electrodes will just do the same as they did in the previous example. The positive electrode will attract the negative ion, and the negative electrode will attract the positive ion. So there we've got our aluminium oxide mixed with cryolite to lower the melting point, and we start to pass electricity through it. Now, as you can see, the aluminium ions are moving to the bottom to the negative electrode. Why are they doing that? Well, that's because they're positive and they're attracted to the negative. The oxygen is moving towards the positive electrode, and as that happens, we get oxygen gas being given off at the top and the aluminium being given off at the bottom. Now, the problem with this process, and you probably will remember this from the video about covalent bonding, the problem is that graphite's made of carbon, and at these high temperatures, the oxygen that forms on the negative electrode will react with the carbon in the graphite to make carbon dioxide. So instead of getting oxygen gas given off at the top, you actually get carbon dioxide because the oxygen gas reacts with the carbon in the graphite electrodes to make carbon dioxide. The aluminium just sort of comes to the bottom and is drained off as a liquid. And during this process, as we know, the metal, being positive, is attracted to the negative electrode where it undergoes reduction, it gains electrons, and also the oxygen, being a negative ion, is attracted up to the positive electrode where it donates and loses electrons, and that is oxidation. So again, it's the same principle as before. Now, the important thing in this process is to realise that we're using electrolysis to split the compound into its elements. Now the graphite, as I said previously, will react with the oxygen to form carbon dioxide, and as a result of that, these electrodes in the positive area will have to be replaced every so often because they'll eventually just wear away. The carbon keeps getting reacted with the oxygen and keeps leaving the mixture, so the electrodes need to be replaced every so often. Right, so equations. Again, higher tier only, you need to know the two equations. Fairly easy, you've just got to learn them. The first one, at the negative electrode, the aluminium 3+ gains 3 electrons to make Al, gain of electrons reduction. Positive electrode, oxygen 2- turns into O2 plus 4 electrons, and that's oxidation. Again, you've just got to know these equations really. Overall equation is 2Al2O3 gives 4Al plus 3O2, and again, as you can see, you've broken the aluminium oxide compound down into its constituent elements there. Right, okay, so the next bit is to give you some other compounds that you've not heard of before, and we're going to look at what they are broken down into. So over here you've got your compound, and then we're looking at what's given off at the negative, what's given off at the positive. So we're starting with lead bromide, which we've already seen. Now again, you've got to have the data sheet here. So lead positive, and we can see that Pb2+ there, and bromide negative. So immediately we know that the lead goes to the negative electrode and the bromine is going to go to the positive electrode. Now the next part, lead chloride, we know that lead's positive, so that's going to go to the negative electrode, and the chlorine is going to go to the positive electrode because chloride is negative. Now in the next example, let's get rid of that over there, the aluminium oxide, the next example is aluminium chloride. Now immediately I go to my data sheet, aluminium is 3+, chloride is minus, so again, if aluminium is 3+ and chloride is minus, then the chloride is going to be attracted to the positive side and the aluminium is going to be attracted to the negative side. My last example is, second to last example, sorry, is aluminium oxide. Again, if I go down to my data sheet, aluminium 3+, oxide is 2-, so the aluminium is attracted to the negative, the oxygen is attracted to the positive. My final example is copper chloride. Again, data sheet, copper, there it is 2+, chlorine, there it is -1. And as you can see, the copper being positive will be attracted to the negative electrode, and the chlorine being negative is attracted to the positive electrode. Hopefully that's given you a bit of an insight into electrolysis. The most important thing about electrolysis is not to be scared of the process. It's not that difficult. Students up and down the country find this quite hard, but if you use your data sheet, you can find out what's attracted where, and always at the negative electrode, whatever's attracted there will 99% of the time be a metal because they're all positive, and whatever goes to the negative electrode always undergoes reduction. Whatever goes to the positive electrode always undergoes oxidation, and that is the key. Right, a good way to remember the idea of where oxidation and where reduction occurs is to use this little sort of structure that I've got on the screen now. What I do is I write the phrase panic down the left, and I write the phrase oil rig down the right hand side. And what happens is panic, positive anode, negative is cathode. So at the positive anode, oxidation happens and loss of electrons happens. And then at the negative cathode, reduction happens, and that is gain of electrons. So immediately then, I know whatever gets attracted to the positive anode will undergo oxidation and will lose electrons. Whatever gets attracted to the negative cathode will undergo reduction and will gain electrons. And that's just a little way to help you remember what happens. So if somebody says to me, during electrolysis, what happens to the aluminium, then all that I do is I look on my data sheet, aluminium is 3+, I know that the aluminium will be attracted to the negative cathode, and I know it will be undergoing reduction and it will gain electrons. And that's how I use that logic. Tied in with your data sheet, you can do that quite easily. So hopefully that will help. Okay, so during this section we're going to take a look at the electrolysis of solutions and how this differs from the previous electrolysis, which was the electrolysis of molten compounds. So remember, when an ionic substance is dissolved into solution, the ions are free to move, so it is allowed to conduct electricity. Now this is the same as before, in the sense that you will have the same ions from your ionic compound that you had in the previous type of electrolysis we've been looking at. However, this time you are now going to have the water present, which gives you two other ions, the H+, which is the hydrogen ion, and the OH-, which is the hydroxide ion. If you look at sodium chloride solution, for example, that means I'll have not only the sodium and the chloride ion, but I will also have the H+ and the OH- ions from the water. Now, just so you are aware, if I take a look at my data sheet, if I'm given sodium chloride solution, I can see on there I've got sodium, which is there, and I've got the chloride, which is there. So those ions are present on the data sheet to help you out. So if they say to you, we're taking sodium chloride solution, you immediately can look on the data sheet and see the charges on the ions. Right, okay, so first of all, just take a little look at this. Starting with the negative ions, it's quite tricky. Because we've got two negative ions, they will both be attracted to the positive electrode. The thing is, only one of them will be discharged. So the order of discharge is very simple. If the ion is in group 7, fluoride, chloride, bromide, iodide, then they take priority over the water ions, which are OH-. So if I have sodium chloride solution, then because I've got chloride ions and I have also got OH- ions from the water, the chloride take priority, and that would mean at my positive electrode I'm going to get chlorine gas. And that's just the sort of order of preference. If I use another example, if I add potassium fluoride and in water, then what I would do is I would take a look at my data sheet, and potassium is K+, and fluoride is F-, so I know that the fluoride is going to be attracted to my positive electrode, and so is my OH-, which is from my water, and I know that the fluoride is higher in the priority than the OH- from the water, so I'll get fluorine given off instead of the water being made. And that's just a little rule to help you out. So the negative ions, if it's in group 7, will be discharged before the OH-, which is most of the cases that you'll get in the GCSE exam. Right, so dealing with the positive ions next, it's very important in this one, because when you've got electrolysis of solutions, you're going to have a positive ion from your ionic compound, which will probably be a metal, and you're also going to have the H+ ion from the water. So you've got to decide which one is going to get produced. Now, to do this, you use your reactivity series, and if there are two positive ions in the solution, then the one with the lowest reactivity gets discharged at the negative electrode. So for example, if I have zinc and hydrogen present in my solution, then I look at my reactivity series and I can see that zinc is there and I can see hydrogen is there. So zinc is higher and hydrogen is lower. so the lowest one gets discharged. So I'm going to get hydrogen gas produced as a result of that, because the hydrogen is lower in reactivity than the zinc. Remember, the lowest reactivity positive ion gets produced. Another example, if we have gold and hydrogen present, gold is lower, so at the negative electrode gold will be produced. Just to confirm that, if I take a look at my data sheet, hydrogen and gold is far below hydrogen, therefore we get the gold produced in our reaction, and as a result that will be attracted to the negative electrode. So to recap, with your positive ions in solution, you're going to have a positive metal ion and you're going to have the H plus ion from the water. If it's in solution, you will always have the H plus ion, but the metal will vary depending on the compound that you're using. So for example, if I was using sodium chloride, the metal ion would then be sodium, but I would still have the hydrogen present because that hydrogen ion is always present with water. So if I've got sodium and chloride solution in water, then it's a choice between sodium, the positive ion, and hydrogen, and of course hydrogen is lower in reactivity than sodium, so that gas is given off at the negative electrode, and that's what you've got to try and remember if you can. So we're going to look at a couple of examples now. Right, so here we've got the electrolysis of sodium chloride solution. Now, sodium chloride is more commonly known as brine solution, and this produces some very, very useful products that are useful sort of for many different reasons, which we'll discuss in a little while. But for now, what we need to realise is that in this sodium chloride solution, we're going to have our sodium, Na plus ions, we're going to have our chloride, which are Cl minus ions, and because it's in solution, we're going to have the water, which breaks up into H plus and OH minus ions. So I've got 4 different ions present in this solution. So what we're going to do, we're going to deal with the positive electrode first. Now, if we look over to the positive electrode, what we'll see is that during this process, I'm expecting the chloride ions, Cl minus, and the OH minus ions to be attracted over to this side. Now the choice then is which of those 2 ions is going to be discharged and given off. Well, remember, if your ion is in group 7, it takes priority over the OH minus ion, and chlorine is in group 7, so the chloride ion will be turned into chlorine gas, which we collect above the positive electrode in this test tube. Now, it's just a case of knowing that if you've got 2 negative ions, the one in group 7 takes priority over the OH minus. If we go to the other electrode, the negative electrode, then what you would expect here is your sodium, which is Na+, and your hydrogen ion, which is H+, both to be attracted to this side. And remember, with the positive ions, we look at the data sheet and we pick the ion that is lowest in reactivity. So we've got sodium and we've got hydrogen ions. Now out of those 2, the hydrogen is lowest in reactivity. So what happens is above the negative electrode we will collect hydrogen gas, not sodium. So what happens here is the chlorine leaves at this side, the H plus leaves at that side, so you've essentially got rid of, out of the 4 ions that we started with Na plus, Cl minus, H plus and OH minus, we've removed the chloride and we have removed the hydrogen. So left in the solution here, we've got sodium and hydroxide ions. So, what's the point of this? What's the purpose of this? So if we look through very, very quickly, we produce a test tube of chlorine, a test tube of hydrogen gas, and a solution left over of sodium hydroxide. Now all of these are all useful. Now the first thing to note with this is the uses of each particular one, because in the exam you will be expected to know why chlorine is used. And chlorine is used for killing bacteria in water, for making bleach, and also for the production of PVC. Hydrogen is used for making margarine and fertilizers, and sodium hydroxide is used for making soap and making paper. So during this process, electrolysing brine, we've actually produced 3 very, very important products by doing that process. And these are quite useful, as you can see, with the products and what their given uses are. Right, first of all, the half equations. Now these are for higher tier only, so at the positive electrode first, the half equation that happens is Cl minus will turn into Cl2 gas, and that will give off 2 electrons, and that is oxidation. So this half equation at the bottom is the one that you need to memorise for the higher tier. It's the half equation for what happens at the positive electrode. And remember, at the positive electrode, oxidation occurs. Remember the previous slide where we did panic and redox? At the positive electrode we get oxidation, so oxidation occurs there. Now, the equation you just need to learn, the second equation you need to know is the one that occurs at the negative electrode. So our next half equation is very simple. It's H plus 2 electrons gives H2, and that's the equation for what happens at the negative electrode, and you need to know both those equations, the one for the negative electrode and the one for the positive electrode. And then just to reiterate, left behind, once you've lost your H plus and your Cl minus, you've got Na plus and OH minus, which is your sodium hydroxide, and that's left in the solution afterwards. The final part of electrolysis that we need to look at is electroplating. Now, electroplating is using electrolysis to coat one metal with another metal. Now, you might do this if you wanted to take some jewellery and you would hear the phrase gold plated. That would mean it's been coated with gold. You would do this to make an improvement on the appearance, but sometimes you can do this process just to protect things. For example, you can coat things with zinc, or you might coat things with different metals in order to protect them from corrosion. So we're going to go through the process of electroplating and then show you 2 examples. So the metal that you want to coat is placed at the negative electrode, so I want to coat over this with another metal. And the coating metal, the metal that you want to actually coat onto the surface, is placed at the positive electrode, and it's placed in the solution as ions. Now the solution is known as the electrolyte, and what happens is current flows and the metal will attract over to the negative electrode. So the metal that you want to coat with attracts over to the negative electrode. And the reason for that is that all metals will form a positive charge when they're in solution, and these positive ions get attracted over it and coat onto the surface of this negative electrode, coating it with the metal of your choice. So we're going to look at 2 examples of this now. Right, example 1, I want to coat a metal coin with zinc. So what I would do is I would take my coin and I would place it at the negative electrode. I would place zinc at the positive electrode, which is there, and then I would use zinc sulfate solution. As soon as I turn on the electricity, and the zinc coats over to the negative side. Because it's positive, it attracts over. Now, just to confirm how we know that, if I go back to the data sheet, I can see further down the bottom of the data sheet that the zinc is there, and zinc, as you can see, is a 2+ ion. So I can immediately see that it's going to be attracted to the negative electrode like any metal would be. So I turn on the electricity and the zinc will coat the negative electrode. And if I take that coin out, then it'll be coated in zinc and it will change appearance. If you do that, you need to know, for the higher tier, you need to know the equations for this. Now the equations are simple. At the positive electrode, which is this one, you start off with the normal metal, it turns into the ion. Again, I know the ion's Ni2+, because I look on the data sheet, and whatever the charge of the ion is, that's how many electrons I would need to add in order to balance the equation. So this equation is Ni goes to Ni2+ plus 2 electrons. And then at the negative electrode, the Ni2+ will arrive, and we add 2 electrons to it, and it turns back into Ni, which is coating the surface of this electrode. Right, our second example, I'm going to get a bit more exotic now. I want to coat a metal coin with silver rather than messing around with zinc. So what I would do is I place the coin at the negative electrode as before. Silver metal would be placed at the positive electrode, and I would use a silver sulfate solution here. And turn on the electricity, and the silver will be coated on the negative electrode. Okay, the longer I leave it, the thicker the coating will be. Okay, so equations. Well, first of all, before I can do any equations, I need to look at my data sheet because I don't know what charge silver is, and it's given here, Ag+. So without looking at this sheet, it's difficult for me to work out my two equations that I'm going to work out in a second. So I know my charge is Ag+. So at the positive electrode, we start with Ag, silver, turns into Ag+, plus 1 electron this time. Because the charge here is only 1+, I only need 1 electron to balance the equation. And then at the negative electrode, the Ag+ is attracted, and when it gets there, it will gain an electron to become silver, which is Ag. Now again, the equations are only for the higher tier. And the most important thing for this is that you understand the general process and you understand why it's done. Remember, we do this to improve the appearance of a metal or to protect it from corrosion as well.